In this lecture, we are still learning chapter 3, and today probably we'll complete this chapter 3. The remaining two sub-chapters are here: principles of congestion control and the TCP congestion control. This one is about the general concept or overall concept about the principles of congestion control here. Congestion. Let's think about this congestion informally. Too many sources sending too much data too fast for network to handle. And that is different from flow control. Flow control is the relationship between sender and the receiver, especially the receiver speed that is considered by the sender. In this case, congestion control, that is meaning about the relationship between senders and the network. And this one is mainly to protect the network from overload of that network by the senders. And we are providing some congestion control to each sender to prevent from that congestion of the network. Manifestation. What is appearing? If there is any congestion, then there may be some lost packets because of the buffer overflow at routers, and there may be long delays. Those are happening because the queuing in the buffers, it is taking long time, thus it is happening. These long delays are happening. This is one of the top 10 problem. Okay, this one is explaining about the causes and costs of congestion. Scenario 1. This one is a very ideal case. For example, here, two senders here, and two receivers here, and one router between them here, one router. And we are assuming this one is containing infinite buffers, and the open link, the capacity is R, and there's no retransmission ideally, but this one is not real in our realistic network because we are using finite buffers instead of infinite buffers. Then why we are using this concept, this example, why we are considering this one? To simplify our explanation. After that, we will consider more realistic situation. Here, we are assuming the rate will be R. If they are sharing evenly, then each bit pipe will use R/2 rate. And if this one is lambda in, that is the input rate, that is the maximum here, R/2. After that, the output will be same to that. And the output throughput, this one is output throughput. The maximum per connection throughput will be R/2. This is the ideal case. If this rate, input rate, that is approaching to that maximum capacity in terms of that bandwidth, then as we learned in the chapter 1, the delay will be increasing rapidly like this. Large delays as arrival rate lambda in approaches capacity. And we are considering one more realistic situation. That means finite buffers. We are considering finite buffers instead of infinite buffers. Then sender and sender may retransmit of timed out packet because there is some dropping because of the finite buffer. And the application layer input, that is equal to that application layer output. Lambda in is equal to that lambda out. Transport layer input includes, but this one is taking care of that retransmission. And this lambda in dash, that is always a little bit more than the original lambda in because there is some retransmission and we should consider that retransmission there's lambda in dash that is more than that original input rate because of that retransmission. And we will consider almost a similar one using the same finite shared output length buffers. And if we know the buffer available here, that is the assumption, perfect knowledge about that. Ideal case, still it is not realistic at all. Send sends only when router buffers available. Then, depending upon that lambda in, the lambda out throughput will be increasing proportionally to that. After that, that is the maximum out of 2. They are evenly sharing. This one is sending more because there is no buffer, then there is some retransmission. Then this copy will be sent again, that is called retransmission. There's always this lambda in dash that is more than this lambda in. Send only descend if packet known to be lost. But we are approaching to the more realistic situation. Packets can be lost, that means dropped at router here because of the finite buffer. And the sender knows when packet has been dropped, only descends if packet known to be lost. Then this one is always below that the maximum throughput because of that retransmission. This one is decreasing that effective throughput. When sending it out of 2, some packets are needed retransmission, thus always that is lower than that. This one is being wasted capacity because of that retransmissions. And this slide may be different from the 7th edition PowerPoint, and I borrowed this one from the 8th edition PowerPoint. And I uploaded already that 8th edition PowerPoint, thus you can refer to that slides. Also, we are considering more realistic, more and more, because that will be more useful. Here we are considering unneeded duplicates. Packets can be lost, as we learned in the previous slide, and dropped at routers due to poor buffers, as we learned already, and that is requiring retransmissions, same. And also we should think more. But sender times can time out prematurely. Sometimes the timeout value is timeout value is so small. There's sometimes that timeout may be happening prematurely. Then sending 2 copies and more copies because of that premature timeout, even though that is being arrived successfully and that is being transmitted successfully, we are sending more. Thus, this lambda in dash, that is increased one, and much more than this lambda in, depending upon that retransmission. Original data plus retransmitted data and duplicated data also we are sending. That is unneeded. Sometimes we are sending the transmission, and that is caused by the error on the transmission. Then that is normal, and we should recover from that error. Thus we should send. But sometimes even though that is successfully being transmitted, we are sending again because of that duplicate packet for that premature timeout, thus decreasing more. That is another waste. When sending at out-of-2, some packets are retransmissions, including needed and unneeded duplicates. Because of the needed retransmission, because of that unneeded, unnecessary duplicates, that final throughput will be decreased. Also, I borrowed this slide from the PowerPoint from 8th edition, and that is expanded more, and it is useful and helpful for better understanding. Here this is same, and because of that wastage, that is a kind of costs of congestion, more work. That means retransmission is required for given receiver throughput, and unneeded or unnecessary retransmissions are required. Then link carries multiple copies of packet, and that is decreasing maximum achievable throughput like this. And another scenario, this one is considering more hosts here, 4 senders here, and the multi-up passes, timeout and retransmit, that is possible here. What happens as lambda in and the lambda in dash increase? Lambda in and the lambda in dash, those are increased, then what's happening? And we are assuming here finite shared output link buffers as a realistic consideration. And we have more bit pipe here, this red bit pipe and blue bit pipe, and this green bit pipe, this purple bit pipe. Our realistic situation is much more complicated than this. We are simplifying and we are trying to understand. Answer is, as read, lambda in dash increases, this one is increased. All arriving blue packets, this one is blue packets by this blue bit pipe. Blue packets at upper Q are dropped, this one is upper Q. And the blue throughput will be 0. Because this one is finite buffer and limited resources. If this one is occupying fully almost, then this one, this bit pipe cannot use that finite buffer because that is consumed, exhausted already. Thus the throughput will be approaching to 0. Thus, this one is the more realistic situation. Another cost of congestion. When packet dropped, any upstream transmission capacity used for that packet was wasted. There's the final throughput will be decreasing like this. That is congestion. Thus we should solve this problem. And let's look at this main topic about TCP congestion control. TCP congestion control. We are using this algorithm or this scheme. This is AIMD. The full name is additive increase and multiplicative decrease. What does that mean? This one is explain about that. We are using this approach. Sender increases transmission rate, that window size, probing for usable bandwidth until loss occurs. And when we are increasing additively, in other words, we are increasing slowly, increases congestion window in the sender side. That is a kind of buffer in the sender side for transmission buffer by on maximum segment size. This one is like the packet, and this one is one segment. maximum segment size every round trip time until loss detected. Thus slowly it is being increased. The storage, that buffer is being increased, and the whole contents of the buffer will be sent when we are sending to the receiver, even without any acknowledgement. And also we are using this multiplicative decrease scheme, cut congestion window, that is sender's buffer size per transmission, that was increased like that, but that will be cut in half after loss. If there is some loss, that means that network is serious, we are assuming. Thus, to protect the network, we are cutting that the congestion window, the sending buffer size, to half, in half. And this AIMD sawtooth, this is very similar to the sawtooth, like this. Okay, let's move back. Probing for bandwidth. This y-axis, this one is about the congestion window, TCP sender congestion window size. You can think this one is the sender's buffer size per transmission. Depending upon that buffer, sender is sending without any acknowledgement from the receiver. Thus, if that buffer is big, then we are sending more data. If that is buffer is small at this moment, then sender can send only a small quantity of the data to the receiver. We are controlling that buffer size. That is congestion control. Then how we are controlling that buffer size for sending? This is being changed like this. It is very similar to the sawtooth. Thus, this is being changed based on this AIMD algorithm, additive increase, multiplicative decrease. You can think this one is being increased slowly, here also increasing slowly and slowly, but when this one is being decreased, that is being dropped rapidly, like our multiplication. Compare addition and multiplication. Addition is a little bit slower than multiplication. With the multiplication, this one is multiplicative decrease. Rapidly it is being dropped. Thus the size of the sender's buffer size for transmission, the size will be reduced rapidly. Thus only this size, the size can be sent to the network. Thus network can be protected. This is additively increase window size until loss occurs. When cut in that case, then cut window in half. Here, that is loss is happening here. Then this one is dropping like this, and we will be learning more about this. And I borrowed the same slide, almost same, but this one is expanding a little more about this. Sawtooth explanation here. Yeah, this one is additive increase. This slow slope you can see. And this one is increasing standing rate by 1, maximum segment size, every round trip time until loss detected. And this one is about the multiplicative decrease, cut sending rate in half at each loss event. Loss event is happening here. Thus, this one is detecting that loss, and depending upon that event, it is being dropped like this rapidly. That is multiplicative decrease. And here, slowly it is being increased, and here the loss is detected. Then how we can detect that loss? That is a question. As we learned already, timer value. Timeout is happening. Timer is timed out. Then we are assuming the loss is detected. And also we are assuming another one. 3 duplicate acknowledgements are received from the receiver, and the sender received that triple duplicate acknowledgement. Then we are also assuming the network is being congested. Depending upon that, we may decrease indifferently. Here, TCP congestion control, AIMD, we learned. And let's move to the next one. If we are using that AIMD scheme, then we can think about the throughput. Roughly, this one is the sender's buffer and the sender sequence number, as we learned in the previous slide about the TCP go back and selective repeat. This is the window, but this one is about the congestion window, sender side. And this side is being changed. See window, this side, whole side, that is being changed. Last byte acknowledged and sent, not that acknowledged in byte, and the last byte sent. Sender limits transmission. Last byte sent minus last byte acknowledged. Here. This one should be congestion window. Always that should be. C window. Below that number, there's this storage size. Within that storage size, and that storage size is controlled by the previous congestion control scheme, AIMD. This C window is dynamic function of perceived network congestion. Thus, this is not fixed value. Thus, this one is not fixed size. Always it is being changed depending upon the situation of the network. We are considering AIMD scheme. TCP sending rate. Here, roughly we can calculate the throughput in this situation. Roughly send a C window bytes, wait round trip time. Thus, during round trip time, we can send without any acknowledgement from the receiver at the same time. Thus, that is the C window. That is the maximum size we can send during this time, round trip time. Thus, this one is rate that can be achievable using this scheme. Okay, let's move to the next. Okay, we look at those AIMD scheme in more detail, especially about the slow start first. When connection begins, increase rate exponentially until first loss event. Initially, we are starting with the size. C window should be 1 MSS, like this, one segment. This one has holding the buffer size, that is 1 MSS, that is C window. And double C window every RTT. After one RTT, this sender will receive some successful acknowledgement, then it is increasing twice. This one will be 2, the double C window every RTT. And after that, this one is receiving successfully the acknowledgement, then it is increasing again twice, then 1, 2, 4, like that. 8, 16, 2 to the power n, it is being increased. Done by incrementing C window for every acknowledgement received. Let's try to summarize. Initial rate is slow, right? 1, 2, 4. But ramps up exponentially fast because that is being increased based on this 2 to the power n. Thus, the later part that is being increased rapidly, that is called exponential increase. Even though that is starting slowly, it is being ramping up exponentially. And how we can detect that loss, that depending upon that loss event, we are changing the C window size. AIMD is doing that based on that loss. Loss indicated by timeout. As we learned already, we are using timer, and if that timer is expired, then we are assuming, the sender is assuming that network is in congestion state. C window set to 1 MSS. Window then grows exponentially, as we observed in the previous slide about the slow start, and it is approaching to the threshold value. We learn about this threshold, then grows linearly. We are maintaining threshold value. After that, our increases, that will be increasing slowly. And if loss indicated by 3 duplicate acknowledgement, we can choose optionally. One is TCP Reno, and another one is TCP Tau. We can choose this recovery scheme on of these. TCP Reno scheme is doing that. Duplicates, depending upon that. Duplicate acknowledgements indicate network capable of delivering some segments. Think about triple duplicate. Think about acknowledgement or duplicate acknowledgement from the receiver. Then network can send the acknowledgement segment to the sender. Thus, that network is not very serious comparing to that timer value out. The C window is cutting in half window, then grows linearly in half. But if there is some timeout, then in this TCP Tau recovery scheme, this one is C window size will be set to 1. In this case, it is not differentiating between them, timeout or triple duplicate acknowledgement. In any case, this one is setting the C window to 1 in this TCP Tau scheme, recovery scheme. Always it is being changed to 1. But in Reno case, timeout is more serious. Thus, in that case, if there is some loss, but that is caused by timer value timeout, then the C window size will be 1. But if that loss is caused by triple duplicate acknowledgement, then that is not very serious. There's the C window size will be half instead of 1. That is the main difference between this TCP Reno recovery scheme and TCP Tau recovery scheme. We will look at this one, and we also will have homework assignment. Let's look at this one. TCP switching from slow start to congestion avoidance. This is congestion avoidance. After certain threshold value, this one is be very careful, and this one is in congestion avoidance state in terms of the state. When should the exponential increase switch to linear? This one is being increased slowly, 1, 2, 4, 8, but rapidly. Later part it is being increasing rapidly. Thus it is called exponential increase. But this one is asking about when this one is being changed to this linear increase. That is this one. This one is slow start threshold value. If this one is over that slow start threshold value, then it will be increasing linearly like that. And this state is called congestion avoidance, because we need to be careful to avoid that congestion. Thus, this one is congestion avoidance state after this SS thresh. That means slow start threshold value. Then, how we can decide this slow start threshold value? Answer, this one is the answer. When C window gets to 1/2 of its value before timeout. Here some loss is happening, and that the C window value is 12, then threshold value, slow start threshold value will be half of that. That means it is being changed to this 6. Thus, this slow start threshold value will be changed depending upon the previous congestion window. When this one loss was happening, that is being considered, and that half of that congestion window, C window value will be used for this threshold value. Implementation. This one is variable slow start threshold. One loss event, slow start threshold value is set to 1 over 2 half of C window just before loss event. Loss event is happening here. Thus 12, thus this one is being changed to 6. This one was probably in the previous case 16, thus this one is 8, even though that is not shown here. And here we can differentiate two recovery schemes. One is TCP Reno, as we learned in the previous slide. Another one is TCP Tower scheme. In the TCP Tower, this one is being increased like that, and some loss is happening here. It is not differentiating whether that loss is caused by timeout value or that is caused by triple duplicate acknowledgement. Anyhow, if there is any loss, then it is being dropped to 1 in this TCP Tower scheme. You know the Lake Tahoe in Nevada State in the United States, that is Lake Tahoe. Thus you can think this one is deep. The Lake Tahoe is really around 300 meter depth, and that lake is very beautiful lake. Many resorts area housing for vacation. Many Californians are visiting there. And this one is about the Reno, and you know the Reno, the city Reno, you can do gambling there, and this Reno is near to that Lake Tahoe, and here Reno is city and no lake like this Tahoe. Thus you can think that is above that Tahoe scheme. Thus it is being dropped to half. Thus this is 12, thus it is being decreased to 6, and from that it is being increased slowly because that is in congestion avoidance CA state. In this TCP Tower case, it is being increasing slowly, exponential increase until threshold, and after that it is in the congestion avoidance state. You don't need to look at this one in detail, and roughly you can think this one. This one is specifying more in detail about the previous explanation and something more to design our real protocol based on this final state machine. Okay, TCP congestion control scheme is based on this final state machine. As we learned, we are using the slow start and congestion avoidance state and the fast recovery state. And here, slow start, it is being increased slowly, and if there is any acknowledgement, then duplicate acknowledgement, that is counting, and it is being changed to other state, congestion avoidance state, if that is over slow start threshold, as we learned. If in this congestion avoidance state, if there is any timeout, then it is dropping like this, and the window size will be half. The slow start threshold value will be half of that congestion window, and the congestion window size will be 1 here on MSS if that is timeout. But if that is triple duplicate acknowledgement, that means duplicate acknowledgement count equals 3, then instead of C window here 1 MSS here, slow start threshold will be same 2 over 2, that means half, and the C window, that is from that slow start threshold, and plus 3, and it is over then that slow start threshold. And here this one is fast recovery state. If there is any duplicate acknowledgement, then it is being increased linearly, and if there is any timeout, then it is assumed so serious, thus the C window size will be changed to 1. From the slow start, when there is any triple duplicate acknowledgement, it is moving to this one. C window size will be divided by 2, and that value will be assigned to this threshold value. And now this one is enumerating the detailed event and action to design the finite state machine. You can refer to this one, but just for reference. Okay, in terms of TCP throughput, always we should think about the performance issue, because all users or any applications are very sensitive to that throughput and performance metric. Okay, here average throughput, TCP throughput as a function of window size, RTT. Ignore slow start, assume always data to send. In this one is window size measured in bytes where loss occurs, and in the AIMD state, in this situation, we can estimate the expected or mean value of that throughput. That means average throughput. This one is roughly, this one is W. Thus this one is half of that, and this one is 75% of that. Thus we can roughly, this one is the average bandwidth, average throughput. TCP futures, TCP over long path pipes. This one is considering the TCP's performance when the bandwidth is becoming huge, path pipes, depending upon the communication technology involvement. Example, 1500 byte segment, and it is 100 millisecond round trip time, and we are using 10 gigabits throughput. Then the window size is this one, implied segment, to maximize that the utilization of that throughput of that original bandwidth. And we are considering the loss probability, and you don't need to worry about this one, just for reference. And this one was described by this message over 30 years ago. To achieve 10 gigabits throughput, need a loss rate of L, very small loss rate. Fortunately, our communication link, that is being very stable because we are using optical fiber, and the speed is becoming faster and faster, and the involvement is so great. Thus, we can consider this kind of protocol's performance, especially in this chapter, TCP's performance, considering our communication link speed. New versions of TCP for high speed, because this TCP was designed and developed in the slow communication link and small bandwidth of the communication link. Thus, we should always check about that, whether that is appropriate or acceptable. Is there any problem? Always we should think about that in the engineering's perspective, engineering's point of view. Okay, let's move to next. Okay, also we should think about other factor about the pennies to provide the equal opportunity or equal pennies to every bandwidth. We should think about this. Penny score. If k TCP sessions share same bottleneck link or bandwidth R, each should have average rate of R over k. But for simplicity, we are assuming we have two TCP connection 1 and connection 2 here. And we are assuming this one is bottleneck router and that capacity is R. And here, using that very simple scenario, we can analyze whether that is fair enough. Two competing sessions. And here, additive increase gives slope of 1. We are using AIMD. Thus, this one is, in other words, whether AIMD is providing pennies or not. And multiplicative decrease throughput proportionally. And this one is equal band share. This one is connection 2 bit pipe throughput. This one is connection 1 bit pipe throughput. And if this one is same to the both of them, then that is equal line for pennies. If that bandwidth is shared like this, then it is very fair to both connections. And we are checking this one in this way, roughly. We are starting and we are assuming in this arbitrary position, here the bandwidth is here like this, that is used by the connection 1, and this one is being used by connection 2. And connection 2 is using smaller bandwidth than connection 1 bandwidth. And now this one is much below than the whole bandwidth because this area is not fully utilizing that bandwidth R. This is the maximum bandwidth. After that, that is not possible, and the congestion may be happening. There's AIMD scheme is working there. Also here, the AIMD scheme is working, but this one is increasing slowly, and this one is decreasing rapidly. That means multiplicative decrease, as explained here. Okay, this one is linearly increasing, and both bandwidths, connection 1 bandwidth, connection 2 bandwidth, those are increased like that. And this is the maximum. So after that, this one should be careful. And there's some loss because of the congestion that may be happening. Then let's assume here some loss is happening here. Then it is being decreased rapidly. That is multiplicative decrease. That means this is the bandwidth at this position. That should be half. This half is like this, roughly. And this is the bandwidth at that point, and that half is like that. This moving to that. And also here, bandwidth enough, thus it is being increased slowly. There's additive increase like this. And also some loss like this. And finally, instead, we can use UDP instead of TCP here. This was explained about that. In other aspects, pennies parallel TCP connections. Application can open multiple parallel connections between two hosts. Web browsers do this. Think about your PC at this moment, and you are opening many browsers together. For example, link of rate R to 9 existing connections, and new applications asks for one TCP, then that will get 10, including this 9 and 1, that will be 10, and they are sharing evenly and in pair way. It seems to be working in pennies. But new application is asking for 11 TCPs. If your application is requesting 10 object and including that HTML file, then it is opening TCP, 11 TCP connections, different connections, let's assume. Then it is single user application, single application is taking and it is consuming among 11 and 9, that is added up to 20. Among 20, 11 over 20 is being used by a new application. That is not fair in this way, in this situation. Okay, let's look at other topic. Even though we are using in TCP source and destination end-to-end congestion scheme by the end TCP transport layer, and we are not considering the notification by the network infrastructure like routers notification, we are not using, but another scheme may be, and this one is explain about that. This one is using explicit congestion notification, acronym is ECN, network assisted congestion control. 2 bits in IP headers, then that may be used. We'll learn this one later in network layer, because this one is belonging to that IP network layer. And especially in this type of service field marked by network router to indicate congestion. Congestion indication carried to receiving host. Receiver seeing congestion indication in IP datagram, set EC bit on receiver to send acknowledgement segment to notify sender of congestion. If we are using this explicit congestion notification and it is being more complicated, actually in our TCP we are not using this scheme, but if we are trying to use this explicit congestion notification, then this is another way. This one, and we need support by the network layer IP like this. Okay, we can wrap up here after completion of this summarization. We learned about principles behind the transport layer services, about the multiplexing, demultiplexing scheme, and the reliable data transfer, flow control, congestion control, and some instantiation and implementation in the internet UDP TCP. Next, we learn about the network layer, and we are leaving the network edge. So far, we learned about the application and transport layer. Those are called network edge part, and we are going into the core part, into the network core part, infrastructure, 2 network layer chapters, and network layer is divided into 2 chapters. Chapter 4 and 5, one is data plane. Chapter 4 is about data plane chapter, and the chapter 5 is explain about this control plane. Approaching to the pennies line. Thus, we are assuming that seems to be working in pennies. A little more about pennies in other aspects. Pennies and UDP. Multimedia applications often do not use TCP because do not want the rate throttled by congestion control. Because congestion control is throttling the sender's transmission. But if we don't want that throttling, then we will not use TCP. Instead, other UDP may be used. This one is explained about that. Let's look at this lecture web page. This one is a single and a simple web page. But this one is containing the bulletin board link here and some downloadable PowerPoint, that is 7th edition. Also, even 8th edition, I uploaded here, thus you can download from this one. And as you are using this Wireshark Lab, PDF is still here. And many other YouTubes are uploaded in the here. Also, those are uploaded in the Blackboard, but the Blackboard is so time limited, and also sometimes that is very busy in terms of the load. There's you can alternatively use this one. Also, I uploaded some reference here, some information about references and some link. Even that interactive exercise that is about chapter 1, chapter 2, even though those are from 8th edition, but the contents are usable in our case, exactly almost the same with the previous exercises. And instead of the previous exercise that is not linkable at this moment, thus we are using this interactive exercise link. And the chapter 1, 2, 3, you can refer to this one. That will be included in the scope for the midterm exam. Later, even for the final exam, that will be considered. Also here you can see TCP UDP client server Python program example. Even though we learned already, I am reviewing here. Let's move to the lecture bulletin board here. And here, as I explained already, we have the URL here. Also, this one is about interactive exercise URL, thus you can click this one, as I explained already. And also, this one is containing the animation and the video. And I'll click this one. And here, we are using these interactive animations and the video notes. And this interactive exercise, this one is not linkable. Thus, instead of this, I am introducing other 8th edition interactive exercises, as I already showed. And here, let's look at these interactive animations here. And also this video note about the TCP congestion. And please refer to these video clips. And this one is explaining about the problem, sketch problem in the chapter, and that is the helpful to answer that, because this instructor professor is explaining about that answer. And I will not go into this one. Instead, I am trying to show this TCP congestion control, because in this lecture we learned about this. And let's look at this one in more detail. After enlarging a little bit more. Okay, this one is explained about TCP congestion, and especially to this animation. Okay, let's look at this one first. TCP congestion control is described in chapter 3 of the textbook. In this interactive animation, we can view how TCP behaves when multiple clients are sending data of the same link. We may add stations. This one is station. We may add more, either before or during the simulation. The default is one station, like this. When the maximum amount of bandwidth is consumed, this one is the maximum bandwidth, and we can change. Is consumed. All of the sending clients reduce their transmission rates depending upon the recovery method. Recovery method, as I introduced already, Reno scheme and the tower scheme. The green background in the graph here, green background graph shows the total amount of consumed bandwidth. The triple acknowledgements button and the timeout button here, triple acknowledgement, timeout button, trigger. Intentionally we can put in this timeout, that loss caused by this one. Corresponding event for that particular workstation. The Reno and the tower buttons set the recovery method for that particular workstation. The sliders can be used to adjust the speed and the maximum bandwidth. We can add more station here, add workstation like this. After shrinking, we can observe more like this, maximum 4, and that is the maximum 1, 2, 3, 4. And each one can send TCP segment through this network that can be sent. And also we can remove the workstation and we can delete. One is the default station number. Okay, intentionally we can put this triple acknowledgement and the timeout here, and also Reno scheme or tower recovery scheme we can. Here start. Here you to single workstation, let's start first. And what's going on? Like this. If I am reducing this one, that is the maximum bandwidth. Thus this one is trying to be in that within that bandwidth, because this is the network is providing bandwidth, available bandwidth in the network. And this station is keeping the TCP congestion rule, and depending upon that rule, that is AIMD scheme as we learned already, this is not going to the above that. That is beyond that bandwidth. And here we are assuming, okay, let's make it high delay like that. And also we can pause here. Okay, let's observe this one. Here this one is increasing slowly, and here this one is with the bandwidth. Then we are assuming the loss is happening. Depending upon that loss, this one is dropping like this. Here we are using tower scheme. This one is going to 1. Segmented size, maximum segmented size is the congestion window size. From this one is increasing slowly and exponential increase here. And this one is probably the slow start threshold value. After this one is in congestion avoidance state, and it is being increased linearly like that. And mid here, and some loss event is happening here. Thus it is dropping like that to 1. So it's congestion window size. That is the tower scheme. Okay, here intentionally we can put in triple acknowledgement and the timeout. Okay, let's start again, resume. And here intentionally I'll put in this triple acknowledgement. In TCP tower scheme, depending upon that triple acknowledgement, it doesn't matter. Timeout, it is always dropping to 1. Even though that is not 1, it is 1. To the bottom, almost bottom, like that. It is not differentiating between them always. But if we are using Reno scheme, then if I am using this triple acknowledgement, then it is dropping to the half, right? And okay, also you can see I am clicking here and make it lower like this. And if I am clicking this one, timeout, that is assumed source series. Thus, it is dropping to 1. If I am using click intentionally, some timeout is happening here, and that is received. And because of that, loss is detected because of the timeout value. It is expired already. That means I am intentionally put that timeout here, then it is dropping like that. If this one is receiving triple acknowledgement, then the network is less serious. Thus, the congestion window size will be half from the current window size, like this. And if I am clicking more and more, it is being half of that previous one. Okay, that's it. And the others, if I am adding more, then we cannot see clearly because it is being mixed together. Thus we cannot differentiate which one is sending receiving timeout, and we cannot differentiate correctly. But in this way, we can observe the complexity of the whole network if those are working together with numerous computers using TCP congestion control, and they are learning based on that, then the actual bandwidth is being consumed in this way, and it is learning in that way. Okay, intentionally we can send some error situation, loss situation, then depending upon that, it is working in that way. For almost 30 years, it seems to be working well enough. Still we are using, and we are using other protocol scheme, and that is explained in the 8th edition, HTTP3 using UDP, and also, and that is not in our 7th edition textbook, that's beyond our topic, but in Korea, global edition for Asia, that is available in the next spring, probably, and hopefully, those who, from next year, we can use 8th edition textbook.